Okay, let me start right away with an independence problem, the pi zero one in the independence problem that I care about and I'm interested in during this talk. So the problem goes like this. So you have some pi zero one statement, and recall that a pi zero one statement is a statement in the form for all x b of x, where b is just bounded formula, so every quantifier in b is just bounded, and T is some arithmetical theory. It can be just the theory of Peano arithmetic or PRA or any other interesting arithmetical theory. And then the problem is it possible, is there any machinery to prove that A, the pi zero 1 statement, is not provable in T? Or even more generally, is there kind of characterization of all pi zero 1 provable statements in the theory T, right? Unfortunately, there is no general machinery to attack this problem. Of course, there are some techniques like the second incompleteness theorem, or at some cases for bounded theories of arithmetic, some sort of techniques in propositional proof complexity, or some translations. But in general, there is no machinery to attack this problem. So to have a general intuition that what I mean by the general machinery, just compare the situation with that of pi zero 2 statements, one level above. So recall that a formula is called pi zero 2 statement if it has the form for all x there exists y b of x y, where b is of course bounded, right? So maybe I have to say something about the characterization. So for many theories T, there is a characterization of all the pi zero 2 statements provable in the theory. So the idea is like this. So first, the thing is that you have to pretend that B is a definition of a function. Of course, it's not true for any B, but you can just translate it, change it, somehow reduce it to this case. And then, B is a definition of a function in the following way, that f of x is y if and only if you have b of x and y. And then for all x there exists y b x y is just the definition, is just the totality of the function f, right? It says that for any x there exists y, so for such that y is f of x. So f of x exists. The value of f exists, right? So now what we want is the characterization of the totality, the probability of the totality of f in T, right? When for some f, the totality of f is provable in the theory T. And the answer is that usually for T, you have some ordinal, the proof theoretical ordinal of T, denoted by alpha T here. And then you say that a function is provably total in the theory if and only if the growth rate of the function is bounded by some function assigned to the ordinal alpha. So alpha measures the growth rate, some level of the growth rate, and if you have the growth rate below that level, then the theory can prove your totality. Otherwise, it is just beyond the power of the theory T. So, given that kind of characterization based on the ordinals, based on the growth rate, then of course it is not that hard to prove the unprovability of some pi zero 2 statements. It is just enough to find a function with huge uh, growth rate for, let's say, beyond just what you can measure by alpha t. And then that function, the totality of that function, of course, is not provable. It is pi zero 2, but it is not provable in the theory T. So this is the usual provably recursive functions characterization of provably recursive functions of some theories T based on the ordinals of the theory. So what I'm saying and what I'm interested in this talk is that is it possible to develop a similar kind of characterization for pi zero 1 sentences, maybe even using some ordinals, characterize all of them, all of the provable ones from the theory, right? Is it possible to do that? Uh, so the first thing to consider is that pi zero 1 is actually a hierarchy of classes, not just one class. So the idea is that if you think about that, a pi zero 1 formula is just for all x and something bounded. And something bounded means that you have many quantifiers, existential or universal, all of them bounded. And therefore, you have the alternation of the quantifiers, and each alternation corresponds to some complexity class. So, of course, then you have different complexity classes all at the same time, and this is not something easy to handle. Therefore, if I want to solve this problem, if I want to find some sort of characterization for pi 0, 1 provable sentences, maybe it is reasonable to just narrow down the problem to the first possible level. And what is the first possible level? It is just the following. The formulas in this form, you have for all x, and there exists the existential quantifier is bounded, of course, and then you have some bounded by some polynomial, of course, and then you have here some polytime computable predicate as the base level. So this is just something easy, and then you have one existential bounded quantifier and nothing else. There is no alternation, no universal bounded quantifier, just this. And of course, it is obvious why it's called total NP search problem, because it is total as we saw before, and then NP search because the definition is NP, right? Bounded the existential in length by polynomial, and then you have polytime. So this is my first level without any alternation. You now I want to capture, maybe based on ordinal or proof theoretical ordinal of T, uh, that when such type of formulas are provable. Okay, before going uh, to the details of this problem, first I have to say something more intuitive and philosophical. So the thing is that you may think that, okay, the formula A, of course, it is pi 0, 1, but in form, it is pi 0, 2 as well, right? It is for all x, there is y, of course, bounded, b of x and y. Maybe we can use pi 0, 2 characterization that we had before, right, to learn something about the formula. The thing is that you cannot. And the reason is that the characterization that we had before for pi 0, 2 statements is based on the growth rate. And here everything is bounded just by definition, right? It is bounded by 2 to r of the length of x. So growth rate cannot be important. Everything is bounded by some reasonably low bound, which is exponential function. So then I would say that the height maybe of the function, meaning just the growth rate, is not important, but maybe the width is. And the width is just the complexity of the computation of the function. Maybe the functions are bounded, all of them, uh, either the provable or not provable, in different theories. All of them are bounded, yes. But then the complexity of computation could be high or low. Maybe when you have a very strong theory T, then you can prove the totality of the NP search problem simply because you can afford that complexity of computation in that theory, and maybe you cannot afford it in the lower theory. So maybe we have to characterize the probability based on the complexity, the width of the problem, the complexity of the computation of the problem may be characterized by some ordinals. And the good news is that it is actually possible to characterize the probability of the formulas like that based on some sort of algorithms uh, somehow indexed by the ordinal, the proof theoretic ordinal of the theory. However, for the sake of this talk, I want to just limit myself to the theory of Peano arithmetic, right? Not all the theories, but essentially what I'm saying is just true for any theory for which we have a reasonable ordinal analysis. So from now on, then I want just to work with the Peano arithmetic. Okay, so here is the informal version of my main theorem. And then after that, we just try to formalize that in some meaningful way and then try to prove that. We will see the sketch of the proof. So first, what is the main theorem? The main theorem says that this statement, the statement of this form that we saw before, is provable in Peano arithmetic if and only if there exists some algorithm to compute y based on x, reading the input x, in the following manner. So the algorithm starts with some initial computation, initial value, say polytime computable function of x, and then followed by some polytime modifications. One modification and then the other modification. Everywhere you use just polytime verifiable modifications till at some point you reach some y bounded by the bound that it should have, and then such that it satisfies B of X and Y. You can find your Y. So the problem is that how long it takes from the initial value and using the modifications to reach your Y. And here is when you use the ordinals, right? The ordinal should be, of course, epsilon naught, the ordinal of the theory PA. So the idea is that to each state, we assign some ordinal such that you start at some ordinal less than epsilon naught. And then whenever you apply the modification, the level goes down, the ordinal goes down, 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 till it reaches zero. And there is exactly the point that via some function, say, applying some last modification or so, then you can find your value y, right? So if something is provable in that form in PA, if and only if there exists, let's say, transfinite type of reduction, which is not really transfinite, which is it is finite because it goes down, but that kind of transfinite type of computation for y from x. Okay, so this is the main form. This is the main theorem. How to formalize that? First, I have to recall some very basic things. The first thing is just the language of PV. So it is a language for polytime computable functions. The idea is that for any polytime computable algorithm, you have somehow one function symbol, but you are using the model of Cobham's recursion using basic functions, composition, and some sort of bounded recursion and notation. But essentially, it is just a language with all polytime computable algorithms as the basic symbols, right? And then you have the theory PV, polytime verifiable, designed by Cook to reason just about the polytime computable functions. If you know what PRA is for primitive recursive functions, it is the same thing for polytime computable functions. So PV is just some, say, quantifier free theory, just very basic theory, equal type uh, theory for polytime computable functions. So the third thing is just the class of functions that I'm interested in. It is 4all1. It's called 4all1. And it contains all the atomic formulas, the negation of the atomic formulas, and it's closed under conjunction, disjunction, and universal quantifier. So more or less, you can have your unbounded universal quantifier, but it should not be used in a negative way, right? And the last thing is that since we are interested in the ordinals and the epsilon naught ordinals, so we need some sort of representation, and of course it should be a polytime representation. So fortunately, there is a polytime representation of the ordinals below epsilon naught. So the idea is that just use the contour normal form and encode that, but in some say careful way, such that then the basic order properties, like that the order is discrete or it is total, and some basic ordinal arithmetic like addition and multiplication, something with some basic properties, all formalizable in PV. So I'm not saying that all the basic things are polytime computable, polytime predicates, polytime functions. I'm also saying that it should be provable, the basic properties in PV. So that's also another thing, but that's not hard, so you can do that. Okay, assuming that we did all of these things, now I want to define a notion that's called a flow. So a flow is my machinery to witness the proofs, and then from a flow, I want to extract the algorithm that we saw before, the algorithm with modifications, right? So it is just the middle auxiliary machine that, if you like, to use for the witness. So what is a flow? Informally, intuitively, a flow is just a flow from A to B. You have two formulas for all formulas, and a flow from A to B is just an ordinal length, of course, ordinal less than epsilon naught, ordinal length sequence of PV provable implications. So you have implication A to something, something to something, something to something, and the whole length somehow intuitively is an ordinal, and each step is just provable in PV. So small steps, simple steps, for some ordinal length from A to B. So this is the intuition behind the notion of flow. And everything in the flow, every formula that we are using should be for all one, just like the formula A and B. So more formally, a flow is just a pair. Beta is an ordinal, at least one, less than epsilon naught, and a formula for all formula, as we saw before, such that the first step is equivalent to A, probably in PV. The beta step is equivalent to B in PV, so A and B. And then in each step in between, if you have H of gamma for anything less than delta, then you can prove H of delta. Of course, again in PV, right? So you can prove something, not just from one before, from everything before. Uh, okay, so that's it. This is the notion of flow. So we want to use my flow to witness the proofs, right? Of course, then we need some sort of calculus for the notion of flow. And this is what we want, the high level calculus, I mean, we want to establish now. So maybe some basic examples. So the first example is that what if I have two formulas, A and B, both for all one, such that A implies B and it's probable in PV. So of course then there's a flow because the flow is just a sequence of implications provable in PV. So one implication is of course an instance, right? So then that's easy. The other thing is just the gluing. So if you have a flow from A to B and one from B to C, then you have one flow from A to C. So why? Because the first is just a sequence of implications, PV probable implications. The length of the sequence is an ordinal from A to B. You have the same thing from B to C, just glue them together, and then you have a bigger sequence of implications, all provable in PV from A to C, right? Of course, for that thing, you need the sum of the ordinals. But if you try to write it, then you see that you need also some sort of subtraction. Meaningful, of course, that from right or left, so I remember now, for the ordinals. And then maybe the last example is that assume that you have a flow from less than delta to less than delta plus 1 for any delta. Then I want to go to some theta for some ordinal. So how to do that? So start from less than 0 to less than 1 to less than 2 to less than 3, right? Just glue all of them together till theta plus 1. And of course, less than theta plus 1 implies theta. And less than 0 is just obvious because there is nothing less than 0. And then you go from gamma to A of theta, right? But this time you have to glue the flows here for different deltas, one after another. So for that, you need multiplication of the ordinals, and if you think and try to write it, then some sort of division from right or left again, it's needed. So this is the thing, and the main idea here is that actually I'm not using anything about epsilon naught. As long as I have some ordinal, and for that ordinal there is some polytime representation such that all the basic ordinal arithmetic is available and provable, the basic things in PV, then we are fine. We can do the same thing here. So the machinery works for any ordinal for which we have that kind of polytime representation. Okay, so now you can prove the main lemma. So what's the main lemma? The main lemma says that if you read all the rules in, say, sequence calculus of arithmetic, of first order arithmetic, the transfinite induction, the usual rules of chord, conjunction rules, disjunction rules, all of them. And if you read the sequence as just the existence of the flow as this, then everything just goes through. So this is the reason why we can witness provability by the existence of flow. So this is the idea. So you can check all of them just one by one, and it's not that hard. So the first, for instance, is cut. So it says that if you go from gamma to delta and A, and gamma prime and A to delta prime, then you can have a flow from gamma gamma prime to delta delta prime. So more or less, the idea is that if you go to A and from A to somewhere, then you can glue them to go from the first to the last, right? So this is the idea. Okay, So we can see then that the rules are respected when we interpret every sequence as the existence of a flow. And this is the heart of the witnessing theorem. So the witnessing theorem says that if you have two multisets of for all formulas, then the implication is provable in PA if and only if there exists a flow from gamma to delta. How to prove that? So the completeness part is easy. The completeness part is when it says that when you have the flow, then the implication is provable in PA. Of course, because the flow is just a sequence of PV provable implications. The length is just something less than epsilon naught. So each step is provable in PV, therefore it is provable in PA. And then you have the transfinite induction in PA, therefore the first implies the last. This is exactly what we have here. So that's easy. So the other one is not that easy. And the machinery that I don't want to explain in detail here is that if you have the implication provable in PA, then you can use some sort of continuous cut elimination to reduce it to provably prove to the same provable claim in PV plus transfinite induction for all formulas. So that type of transfinite induction should be easy for that complexity that we are working with. And then we have to design a sequence calculus for this theory, for the theory PV plus transfinite induction, and then eliminate the cut, the free cut actually, and then it means that when you have a sequence of for all formulas provable, then everything is for all in the proof, and then you can use induction on the length of the proof to show that whenever something is provable, then there is a flow for that. And this is the main idea of the proof. It is just complicated, but not that much. So this is the witnessing theorem. It says that there exists a flow if and only if the implication is provable for all formulas. And now we want to use this witnessing theorem to prove the main theorem that we like. So this is the main theorem. This is the formal version of the main theorem. First, I have to explain what does it mean. So the first part is obvious. This type of formula is provable in PA if and only if the second part is new. So it is the formal version of the algorithm. The data of the algorithm consists of some polytime functions, I, N, P, and Q, and a predicate G, which is polytime predicate. Read this G as at the stage gamma, Z is the result of the computation or the witness, the current witness, right? So then it says that you are starting at beta, and I of X is the witness, the initial value, and then you have some sort of function Q, which is operating on the ordinals, and then it reads gamma and it provides something less than gamma, of course, if gamma is not zero. And if gamma is not zero, then if Z is the witness for the gamma level, then the modification N is the witness for the level Q of gamma, which is lower, right? And then you go down, down, down by the modifications till you reach zero. And if you have a witness at the level zero, then you can use the function p to find your y. And this is the bound, right? So, sorry, this is just the bound, right? So this is exactly the formal version of what we saw before. A sequence of modifications starting from I and then go down till you reach zero. And then after one point, you using P, and then you have your answer. So these two guys are equivalent. How to prove that? The proof is easy. So first note that PA proves this statement if and only if this statement is provable in PA. It is just a logical equivalent. It says that for all y bounded by this bound, negation b implies but. So why bother to transform it in this way? Because then both of these guys are for all one, which means that then we can use the witnessing theorem. By the witnessing theorem, now we see that this is provable in PA if and only if there is a flow from this to but. What is a flow? Flow is just h and beta. So h is for all one, right? So then it is in this form for all z, something polytime predicate, something quantifier free. And then these are just the definition of the flow. The first is equivalent to the zero, the beta, the last is equivalent to but, and each time less than delta implies delta. But if you think about this, you can see that at each point, at each bullet, you have for all implies for all. This is the main form. Therefore, you can use the Herbrand theory. You can witness one for all with the other because one for all is actually the existence, right? And then by these functions, you can have your modification, your initial function, your Q function, all the functions that we saw before. I want just to explain one of them, but the rest is just similar. So think about this, right? If you define G as the negation of I, and if you want to witness this Z because it is existential, then you have to witness it by some polytime function, let's say I of X, and then it would be negation of I be beta X I of X, exactly as you have here. So the rest is just similar. You have you read this Z, witness this Z by the N function, the modification function, witness this gamma by the Q function, you read this Z, witness this Y by the P function, and so on, so forth. So this is the main statement. Therefore, to sum up, a statement of that form is provable in PA if and only if there is some sort of modifications ordered by ordinals, and the proof needs to go from PA to some basic theory via the flows, some sequence of implications, and then transform that implication, each implication using the Herbrand theorem because it is provable in PV. So thank you very much for your attention.